let us look at an example problem. So, suppose if we have a concentric tube, which is what you had in your lab experiment, but this example is slightly different from the experiment that you have done in the lab. Okay. So, the diameter of the inner tube is 25 millimeters and the diameter of the outer tube is 45 millimeters, and you have oil which is flowing at 1.1 kgs per second at 100 degrees C in the outer chamber, and the oil leaves at 60 degrees C. So, clearly that is the hot fluid, and we have cold fluid which is flowing through the inside of the tube, which is water, and it is flowing at 0.2 kgs per second mass flow rate at 30 degrees C. Okay, and that is what is given to you, and some properties are given. We will come to that later. So, the question is find the tube length. Find the tube length. So, how do we address this problem? We need to find the tube length. Okay, we need to find the length of the heat exchanger. So, that is L, that is what we need to find. Anybody? How do we start? Yeah? Yes. We want to find Q. So, if we know Q, Q is UA delta T LMTD. So, if we know U, if we know delta T LMTD and Q, we should be able to find the area. So, the area will tell me, from area we should be able to find out what is the length of the heat exchanger. What are the properties that we know already? What are the quantities that we already know? Yeah? Do we know Q? Yes, we know. This is equal to m dot Cp hot fluid into Thi minus Tho. We can calculate that. We know that. Delta T LMTD, do we know that? How? Okay. So, we do not know what is the outlet temperature of the cold fluid, but we know m dot Cph at steady state. This should be equal to m dot Cp of cold fluid Tco minus Tci. So, from here equating these two, we should be able to find out what Tco is. So, the first exercise is find Tco, and Tco is about 40.2 degrees C. I didn't list the property. So, Cp of oil is 2131 joule per kg Kelvin. This is oil, that's for oil, and the viscosity is 3.25 into 10 power minus 2 Newton second per meter square, and the conductivity of oil is 0.138 watt per meter Kelvin. Okay, and that for water, that's for water. The Cp is 4178 joule per kg Kelvin, and we have mu is 725 into square, and the conductivity is 0.625 watt per meter Kelvin, and Prandtl number is given. Prandtl number is 4.85. Okay, so that is Prandtl number. So, all the properties are given, so we can immediately find out what is Tco. So, we know Q, we know delta T LMTD. Okay, so we need to find U, the universal heat transport coefficient. How do we do this? Okay, so So 1 over u is 1 over H naught plus 1 over Hi. So, I am assuming that wall resistance is negligible. And the wall thickness is small. So, I assume that the wall thickness is small. So, I assume that the outside and the inside area of the tube which is present inside are approximately the same. So, now we need to know what is H naught, we need to know what is Hi. How do we find them? So, we can get the correlations. So, the Reynolds number would be for the inside will be 4 m dot by pi di into mu. So, that is about 14,050. So, this is for the inside, okay, to calculate Hi. So, the Reynolds number of the flow which is flowing through the inside tube is about 14,000. So, clearly it is a turbulent flow. Which correlation should we use? Dittus-Boelter correlation. So, that is what you used in your lab. Use the Dittus-Boelter, and that is NUD, it is 0.023 RED to the power of 4 by 5, Prandtl to the power of 0.4. So, from here we find out that the heat transport coefficient Hi is 2250 watt per meter square Kelvin. Okay. So, that is the inside heat transport coefficient, and then similarly we can find the outside heat transport coefficient. So, that is for HO, and it is an annulus. So, the RED Reynolds number is given by rho um into divided by mu. So, that is the effective diameter. Okay. So, we find that, and so that will be about 56, it is a laminar flow. So, remember that we did not look at the correlations for concentric cylinders. So, one could actually do that, it is there in the text, but we did not go over it in this course for want of time. DH is the effective diameter between the two. So, you look at the, so you know what is the area of flow, correct. So, pi d, the outer diameter minus the inner diameter. So, using that you can find out what DH is. So, there if you assume it's laminar flow and you assume fully developed conditions, so the Nusselt number is constant for that, and it's about 5.56. That's the Nusselt number for that system, and from here we can find out HO is 38.4 watt per meter square Kelvin. So, that's the heat transport coefficient for the exterior of this tube, okay. And so, now we know U, we know delta T LMTD, we know Q, so we can easily plug it in the expression. So, U is 378 watt per meter square Kelvin, and L is given by Q divided by U into pi into D into delta T LMTD. So, that is given by 66.5 meters. Is that a reasonable number? 66.5. Yes, no, no, not at all. We have a tube which is 25 millimeters, which is just 2.5 centimeters, which is this much, and it's 66.5. Why is the prediction wrong? The wrong prediction, right? You cannot have a heat exchanger with a 66 meters. So, what's wrong? It's 2.25 millimeters, that's 2.5 centimeters, that's this much, and you have a 66 meters long. Is it possible to flow water with a reasonable pressure? You will have a huge pressure drop. So, it's a completely unreasonable number. So, how do we handle this? So what will be the first question that you would ask if you get such kind of unreasonable numbers? What are the different types of heat exchangers? So the first question I would say is you should never use this kind of a configuration. You would require 66 meters of construction if you want to use this kind of a heat exchanger for exchange, and this is a pretty realistic system where the temperature differences are not unreasonable, and water is a constant, water is a very normal fluid which is used for heat exchange. So if you look at any industrial process, it's like you conserve water, you convert it into steam when you want to cool some fluid and use that steam to heat something else. So water is a very constant fluid, that is normal fluid which is used in the industry for heating and cooling purposes. So that's not an unreasonable fluid. So the real problem is this is a wrong configuration. Never use a double pipe counterflow is not the correct choice. It's not the right choice for this problem. It's a good choice, maybe a good choice for some other fluid, but definitely not for this system. So you really need a different type of heat exchanger to actually achieve this extent of heat transport for the conditions that's given. If counterflow is worse, parallel flow is even worse. It's more worse. It's worse, So you never want to use any of these double pipe configurations for such kind of a heat transport problem. So this is where using these correlations and trying to estimate the design plays an important role. So if you do not estimate what should be the approximate length or the dimensions of the heat exchanger, you will never be able to decide whether you are doing an efficient job here. So you will end up making a very expensive heat exchanger, but you are just not getting the best out of it. So that's an important point. Alright, so what we will do next is we look at some special cases. I will just sketch some of the temperature profiles, and then we will move on to the log mean temperature difference for shell and tube heat exchangers. Okay. So the first case we will look at, where you have a condensing steam or condensing fluid in one of the chambers. So if you have a double pipe heat exchanger, okay, so you have a double pipe heat exchanger, you have some fluid which is flowing through these two chambers, okay, and you could always have a hot fluid, okay, which is basically a condensing fluid. So the temperature of the fluid inside the heat exchanger will remain approximately constant, because it's the latent heat which is actually being used to heat up the fluid which is flowing through the internal tube. Okay. So supposing if this is my hot fluid and this is my cold fluid, so the hot fluid, it liberates the latent heat which is present by changing its own phase, and that heat is now transported to the cold fluid which is being heated up. So therefore, so supposing if I have a parallel flow, so that's my hot fluid inlet, and that will be my cold fluid outlet temperature. So you can have a situation where the temperature is almost constant in one of the chambers, and that's a typical case when you have a condensing fluid. What's the opposite of that? Cold fluid evaporating. It's sort of obvious to guess that. So you'll have a cold fluid which is evaporating, so which is at a constant temperature, and you have a hot fluid which is actually being cooled, and this is the Tc. This is at a constant temperature because it's being evaporated or it's being boiled, for example. Okay. So that's a special case. And the third one is a little bit more interesting, little bit more interesting is a situation where you have the capacities are constant or equal. The cold fluid is equal to m dot Cp of the hot fluid. So you can always have two different fluids and you can adjust the mass flow rate of the fluid so that m dot Cp is same for both the chambers. You can always do that. Okay. Now what will be the temperature profile? Let us say it is a counter flow. I want to draw the temperature profile for this heat exchanger. Delta T is constant, so that is easy to guess. So you will have a constant delta T. So supposing if this is hot fluid, THO, THI, TCI and TCO. Because the capacities are equal, okay, so Q is m dot Cp into the temperature difference between the two, inlet and the outlet, and similarly for the hot fluid. And so one could guess that the temperature difference along the heat exchanger will actually be constant. What is delta T LMTD here? So remember the expression for delta T LMTD? Delta T LMTD is delta T at one location minus delta T at the second location divided by ln of the ratio. What is that? So this is the expression for delta T LMTD, we know that, and we know that the temperature difference remains constant. So what is the delta T LMTD that we should use? This is not the one, cannot be this, cannot be this. So what is the problem? It is 0 by 0, you cannot have this. So what is the delta T here? It's delta T actual itself, okay. So if you actually go and do the derivation of the delta T LMTD rigorously by assuming that these two are constant, you will find out that delta T LMTD is equal to, basically what it means is that you don't require a log mean temperature difference to characterize this problem. So the temperature difference that you should use is either of these two. So that plays an important role in designing your heat exchanger. If you can actually decide your mass flow rate such that the m dot Cp of the cold and the hot fluid are same, then you have got an important property. You are able to now predict what is the temperature profile inside the heat exchanger, which we cannot do on all the other cases. We do not know what is the exact temperature profile. Note that all these are just sketches. So in this case, we should be able to predict, or we should be able to estimate what is the approximate temperature difference at every location inside the heat exchanger. That plays an important role in heat exchanger design. Okay. So the correct temperature difference that you should use is the actual temperature difference either at the inlet or the exit of the heat exchanger. So next we are going to look at what is the delta T LMTD for shell and tube heat exchanger. Okay. So here the nomenclature I will use is, when I put S, it stands for temperature on the shell side, and SI stands for the shell side temperature at the inlet to the shell, and TSO stands for the shell side temperature of the stream that is actually going out of the shell side, and similarly small ti and small to. Okay. So this stands for the shell side fluid, and this is for the tube side fluid. For the tube side fluid. Okay. So now it turns out that the delta T LMTD for a shell tube heat exchanger, it's basically some fraction of the delta T LMTD for counter flow. Okay, delta T LMTD for a counter flow which is exactly at the same temperatures. Okay, so it turns out that it's a certain fraction of that. but what I am going to simply sketch is what is this fraction f, and from practical point of view, how can you use this f in estimating the delta T LMTD for a shell and tube heat exchanger. Okay. So, in order to do that, we need to define two quantities. Okay. So, one is called the P, which is I think called the thermal efficiency or the temperature efficiency, defined as and that is given by the difference in the shell side temperatures divided by the maximum temperature difference. Okay. Now, I would not like you to stare at the denominator of this expression here. This is the first time you are seeing a difference between the inlet temperatures of two different streams. Okay. So, the maximum possible temperature difference is Tsi minus Tti, where S stands for the shell side and T stands for the tube side. So, difference in the inlet temperatures is the maximum possible temperature difference in the heat exchanger. That is the theoretical maximum. Okay. Now, in fact, in a short while, when we go to epsilon NTU method, we will actually be using this concept of maximum possible temperature difference to define a quantity called theoretical maximum possible heat transport. Okay. So, we have not looked at that so far. So, we are going to see how to define or how to find out what is the maximum possible heat transport rate. Okay. So far, all we know is what is the net heat transport rate in the hot fluid. We know what is the net heat transport rate in the cold fluid, which is equal when it is a steady state, but we do not know what is the theoretical maximum possible. So, only if we know what that is, we will be able to define some sort of efficiency. So, here the temperature efficiency means the difference in the inlet and the outlet temperature of the shell side fluid divided by the maximum possible temperature difference. Okay. And then one needs to define another quantity called R, which is the relative thermal capacity. So, that is sort of easy to realize what it is from the definition. It is basically the ratio of the capacities, or it is defined as Tsi minus Tso divided by Tto minus Tti. Here we have assumed that the shell side fluid has hot fluid and the tube side fluid has a cold fluid. It does not matter how it is, because the minus signs will always cancel out. So, that should be equal to m dot Cp of the tube side fluid divided by m dot Cp of the shell side fluid, once again assuming steady state condition. Okay. So, this factor F, which is basically the delta T LMTD of the shell tube heat exchanger divided by delta T LMTD of a counterflow, equivalent counterflow. Okay. So, if I sketch the graph between the R, which is the relative thermal capacity. Okay. So, what I would see for a fixed P, so note that these expressions have all been derived. We are not going to look at these expressions in this course, but the general behavior is for a given specified P, okay, for a specified value of P. So, what you get is this kind of a profile, where F goes from, what is the range for F? 0 to 1. The same temperatures, you just have a counterflow configuration, that is all. The area is same. So, the net area or that net heat transport area that you have is matched with the counterflow, the corresponding area. So, what it means by saying equivalent counterflow with same temperatures and same area, that is very important, same temperatures and same area. Okay. So, now as P is decreased, okay, So this is the, so what is found is this is a kind of profile that you will get for this fraction f. Okay. So as you decrease p, you will go closer to the origin. So now what it simply means, and note that everything, all of these, they start from 1. Okay. All the expressions for different values of p, they all start from 1. Okay. So which simply means that when p goes to 0 and r goes to 0 or r goes to 0, either of these two, the f will tend to, f will go to 1. Okay. So which means that the limits for shell and tube heat exchanger, in fact this actually comes from the expression for the delta T LMTD, but what's important here from the course point of view is to realize that the upper bound for the delta T LMTD of a shell and tube heat exchanger is essentially that of the delta T LMTD equivalent, delta T LMTD of an equivalent counterflow configuration which has same temperature and same surface area. Okay. In fact, same area is not relevant from the calculation point of view, but you must understand that that's very important. Okay, because remember that for calculating delta T, you really don't need area, you only need the temperature differences. But it's important to say that when it's equivalent counterflow, it means that the area of heat transport is also maintained similar. Otherwise, you cannot expect the same temperature difference to occur in a real situation. So this has been worked out. So this kind of graph has been worked out for all kinds of shell and tube configurations. So we will not go over all of them, but all these graphs are all available. They are all available in tabular form. So the f is available for 1 shell pass, 1 tube pass. It's available for 2 shell passes, 1 tube pass. Is available for 1 shell passes, 2 tube passes. So all kinds of configuration for which this fraction f is available. It has all been worked out, and nice tabular forms are available. They're all available in terms of graphs. So it's very easy to find these numbers. Okay? And it's routinely used in industrial settings. Remember that shell and tube heat exchanger is actually the workhorse of heat exchange process in any industry. Most of the heat exchangers you will see will be of that configuration. So this has been worked out for almost all possible combinations of shell and tube heat exchangers, and there's no need to go over it again and again, but it's just important to realize that it's the fraction of the counterflow, and counterflow is like the upper limit for shell and tube heat exchangers. That is correct. So it has both co-current and parallel. Now what it turns out is that the co-current and the counter-current flow is the best mode, right? Because for a smallest area you can have maximum heat transport. That's why counterflow is like the upper limit for shell and tube.